with that. So if I have a situation, let's just go to the simulation, might just be the easiest way to look at it here, where I have basically two wires that are next to each other, right? And they have currents going through them, okay? What we're saying is that if I have this scenario, we're expecting each wire to receive a force on it. So let's just kind of chat through why that happens again here, okay? So if you look at a scenario like this, like you have like wire A, you have wire B, okay? And what we're saying is that when I put current through a wire, that wire has a magnetic field surrounding it, okay? So let's just focus on A to start with. And if A has some current going through it, we're going to say it's got a magnetic field around it because of that, where on the left side, this is coming out of the board, and on the right side, it's coming into the board. And I'm using right-hand rule number 2 to do that with, right? Where my thumb is up and I'm curling my fingers around that wire, okay? That also means this magnetic field would extend over into here as well as being into the board. And so now what we say is, okay, well, now I bring a second wire in, and it's wire B. And wire B also has some current moving through it. Let's say it's moving up as well, okay? Because you put a wire with current in a magnetic field, that wire has to get a force. And so what force does B get, right? That's the question, okay? Well, if we're thinking about forces, remember, that's when you have to go back to right-hand rule number 1. Okay, so remember, anytime we deal with forces, we're doing right-hand rule number 1. If there's no forces, and we're talking about induced magnetic fields, that's right-hand rule number 2. Okay, so what direction is the force on B? Okay, well, I've got a magnetic field into the board, I got some current that's up, and my palm tells me the direction of the force. In this case, wire B would get a force pointing it to the left. Okay. All right. Questions on that part of it? That makes sense. Okay. So we will see this happening. Now, would wire A also get a force on it? Yeah, it would. You'd have to figure out the magnetic field that B produces, and then how does wire A behave? You guys probably saw the pattern here a little bit. If the currents are in the same direction, okay, the wires actually get pushed together with the forces. If the currents are in opposite directions, the wires get pulled apart. So kind of how that ends up working. Why is this important in the real world? Well, have you ever looked at high voltage power lines and wondering why do they have to have such a big tower and the wires are so far apart? This is one of the reasons why, right? We can't have these wires right next to each other. They get forces. And especially if you have high voltage, high currents going through them, they get a lot of force on them. And so we don't want them coming together or getting pushed away because that would be snap the wire, right, type of thing. Okay. Here's another question. Let me clear this stuff off of here. If I just say have a single wire, I'll just go here and let's just say I've got a single wire, okay? So here's my wire and I got current going up, okay? And I do the right-hand rule number 2 and I say, okay, well, I'm going in on this side and I'm coming out over here. Does that wire get a force then from that? It does not, right? You cannot get a wire cannot get a force from itself, okay? So yes, it's inducing a magnetic field around it, but that magnetic field doesn't put a force on that particular wire. Okay, you need 2 wires in order to experience this. Okay, that's another question that I wanted to throw out there. Okay, now we good on the 2 wire thing. Okay, you'll see some stuff on your homework with it too. Okay, so make sure you're working through 19B. If you look on the website, there's no quiz right after 19B. We're going to do 19C starting tomorrow. And then we'll do a 19B and C quiz together because 19C is kind of short. So, okay? And all that homework, you can just do all of it together on the same paper. So, all right, here's the last thing, and this is what we're going to talk about today, okay? If I happen to have a circular loop of wire, okay? If I were to do right-hand rule number 2, and let's say the current, in this case, is moving in a counterclockwise direction. This is what I want you to get in your notes here, okay? So draw that diagram while I'm talking here. If that's the case, what direction is the magnetic field that gets produced in this circular loop of wire? Well, you can see I already drew the first part of this on here. If I come over here on the right side of my loop and point my thumb up, because that's the direction the current's moving, I can feel or see how I would curl my fingers around that loop of wire, and I would do it in such a way that I am going in on this side and coming out in the middle. Okay. What about if I move up to the top up here? What direction is the magnetic field up there? We'll do the right-hand rule number 2 again. So my thumb would now be pointing more to the left, and I curl my fingers around the wire. I'm still going in on the top, and I would be coming out in the middle. Is that going to be the case all the way around this loop, where I'm going to have the magnetic field always pointing in on the outside and coming out in the middle? Yeah, it should. Okay, so I can fill the rest of this in here just for funsies. Okay, all right, it would look something like that. Okay, what kind of magnetic field am I going to produce in the middle here? Well, it should be a pretty strong one, right? Everything's pointing in the same direction. So those magnetic fields would all be adding together, right? This is a way for me to really produce a strong magnetic field. Okay. Now, this is just true for one loop of wire. What if I do this with 100 loops of wire or 1,000 loops of wire? It's not hard to imagine or to do. I can actually produce a really, really strong magnetic field doing this, okay? And so this is what's called a coil, or sometimes referred to as a solenoid, okay? And this is what you're going to be doing in your lab today, okay? Today your solenoid is going to be a slinky, okay? It's an easy, fun little toy, and also great for creating strong magnetic fields, okay? Now, we're not going to create super strong magnetic fields because we have to be a little bit careful about how much current we put through the slinky. But I'll show you here in a minute, there are ways that you can create very large magnetic fields using this principle, okay? All right, so let's say this is my solenoid here, okay? And let's say this is the magnetic field that's being produced. And if you look in the middle here, you can see that the magnetic field is moving from the right to the left as I look at it. Okay. They could ask this question: what direction then is my current moving through this wire? Okay. In other words, how would I expect the current to be moving? Okay. Well, if you think about this, okay, let's say, let's just take this right edge here. Let's just say, okay, well, let's say I assume the current is moving up the wire like this. Is that correct? Does that match what you see for right-hand rule number 1? Or excuse me, number 2. Excuse me, because I'm doing fours here. Number 2. Maybe it helps if I continue it curving up through the top, something like that. All right. So if I go up, right, you have to think about, okay, I'm going to be coming out of my. I think that here's my wire. I'm going to be coming, in the middle and coming out like that. Is that actually what I'm seeing here? Okay. Or is there a different way that should be oriented? Okay, let me get the lines off there. Okay, so this is kind of hard to visualize. Like, I usually like to think about like what's going on at the top of the loop, because that's an easy one to kind of think about. And so if my wire at the top here is like this, I'd be kind of wanting to curl around this way. So I kind of want the current coming around like that. Does that make sense? Yeah. Okay. All right. Which means I'd want the current to be moving like this down my wire, right? So you kind of have to think through that a little bit and just think about how that's curling through there. So actually that means if this was positive negatives, right, this would be the negative side of my battery or my power source. This would be the positive side here, okay? All right. So this is one of the things we're going to look at today when you do the solenoid with the slinky. Is you need to think about what direction is the magnetic field that you're producing. Okay, how's it moving through that coil? Okay. But again, we can actually produce a fairly strong magnetic field in between there because everything's all pointing the same direction. It's all adding together. Okay. Now, just a couple quick notes on this. In the real world, what they'll actually do is, rather than having air through there, they discovered if you put a piece of metal in there that can be magnetized, like, iron or lead or something like that, then you can actually produce an even stronger magnetic field because you're actually magnetizing the metal as well with that, okay, which is also kind of a cool thing. So you can actually create a really strong electromagnet doing this. Okay. There's a question in your lab today. You may or may not get to it. It's at the very end, where we actually have this picture in there. This is a picture of a very, very strong electromagnet that was at the particle accelerator at Fermilab, which is just outside of Chicago. One of the places where they did a lot of cutting-edge physics research in the 1970s, 1980s, where they were discovering things like different types of quarks. You may remember us talking about those briefly. And so this can really produce a very strong magnetic field by A, having a lot of coil there, B, putting some metal in there, and of course, the other component is, hey, let's put a lot of current through there at the same time, right? So all three of those things combining together, you can produce really strong magnetic fields, which are really handy if you want to accelerate some particles. Okay. All right. So today you're going to kind of do this for yourselves. So let me show you what you're going to do here on this lab for 19.6. And again, you can use the graph paper there because you are going to do a graph with this. So that's why I gave that to you today. Okay. But basically what you're going to be doing is you're going to be creating your own solenoid or coil using the Slinky. Okay, first of all, the Slinkies, yeah, they're fun little toys. If you need to get your fix and play with it for a few minutes, that's fine. Don't jump rope with it, though, or anything like that, okay? We already had to reprimand one student today for that, so don't make me go down that road again. Third period, they're usually such a nice, quiet group, but not today. Something about Slinkies to set them over the edge. But yeah, don't get them like all twisted and tangled together, because we need these, all right? But yeah, they are fun. What you're going to do is you're going to hook up some current to it. Now, today you're going to be seeing at the stations around the outside, there are the variable power sources that we've used before. It talks about this in the preparation, but we want to make sure that we don't put too much current through these, okay? I think 1 amp is the max we ask you to keep this at, okay? So there's enough resistance in that coil where if you keep it below 1 amp, it'll be fine. But remember, turn the knobs of voltage and current counterclockwise. We'll take them all the way down to 0, and then just slowly turn each one of them up till you get a little bit of a reading there, okay? You're also going to be using a new sensor that we haven't used before, which is a magnetic field sensor. Let me come over here and grab one of these real quick here. And just so you can kind of see what it looks like. The magnetic field sensors will plug into these LabQuest 3s, so it may already be plugged in for you. And the sensor itself is this clear tube. And the clear tube has a white dot on it, and that's important because that'll be what you want oriented. It talks about this in the lab, but the white circle should be facing the south pole of your magnetic field. So remember, your magnetic field runs from north to south, so be pointing it kind of towards the direction of the south pole. That'll help you get the best reading. You can also zero this before you put it into the coil, which will also help. On the lab, touch the part where it's giving you the reading, it'll come up with an option for zeroing it. So let me know if you need help with that. Lastly, make sure there's a little switch on here that's really scientific. It's low and high. We want this on the high setting. This will amplify the magnetic field. You'll get a little better readings on your data that way as well. Okay, we're not really producing very strong magnetic fields. And the other thing that we have to battle here a little bit is this thing reads all magnetic fields. So you want to keep this away from other, like even the power source, try to have a little bit of distance there because the wire of the power source is producing a magnetic field. We're also in the Earth's magnetic field, can't do anything about that. But that's where the zeroing will help that a little bit because the Earth's magnetic field is just there. This will read that field, but if I zero it, it kind of helps kind of minimize that. So those are some things there just to be aware of. Lastly, I should mention, when you take your readings, it's going to give you a reading in a lowercase m, capital T, okay? This is a millitesla. So this is actually a millitesla is a thousandth of a Tesla, okay? So like a millimeter is a thousandth of a meter, okay? So, if I have 2 milliteslas, really that's like equal to 2 over 1,000 Teslas, okay? So it's not very many, okay? And so whatever readings you get, make sure you're dividing those by 1,000 to get it into a Tesla unit. Okay. All right. Here's your goal though with what you're doing. Okay. Your goal is going to be to actually figure out a value for the constant that is in the equation for induced magnetic field, and that constant is the mu sub 0 constant. Let me get my pin back on here. Okay. So we talk about this equation in the lab. You might say, well, that's a little different than the equations we've been looking at. It's not on your sheet, and that's correct. We're kind of simplifying this a little bit for a solenoid or a coil. And when we think about the magnetic field through the center of that, we actually don't need to worry about the radius distance r, because we've got a wire all around us, essentially, okay? But what does matter is the number of coils that we have. That's going to play a role in how strong that magnetic field is. So you'll see in here, we introduce lowercase n to you, which is the number of coils per meter. So you will need to count that, okay? Now, that doesn't mean you have to take a whole meter and count a full meter's worth. In fact, I don't even think you probably want your slinky to be that long, probably. But you just need to take a segment of it and count how many. If it were a meter long, how many coils would it be? So use your smarts there. You guys can figure that out. Okay. But honestly, if you just stretch the slinky out a little bit, I mean, a half a meter is probably plenty. Okay. But you do want to count the number of coils per meter. And then once you get that, keep that constant. Don't change that. Okay. And so what I suggest is just spread your slinky out, and there's some tape up here. There may be even some at the station still. And just tape it down so it stays in one place and at a consistent spread there. Okay. So that's one thing you need to do. The other thing you need to do then, of course, is measure the magnetic field. That's what this sensor does, okay? And the current, which is, of course, you can see that on the power supply, okay? So you will take data of magnetic field and the current, and you probably need about 5 or 6 trials of those. So 5 or 6 different pairings of magnetic field and current. And then that will allow you to solve for this mu sub 0. That's your goal, is to figure out what that is, okay? Now, to compare, if you go back here to this table of info here, this constant is on there, so you can kind of get an idea, maybe. If I can, I'll try reloading here. You can get an idea of what this should end up being here. There it goes. Okay. And so we're talking about this constant right there. It's 4 pi times 10 to the negative 7th, right? Okay. So it's not a very big number that we're searching for here, okay? So in the lab, we ask you to create a graph with your 5 or 6 data points and then try to do a best fit line, do the slope thing again, like we've done many times, to see about getting this value, which is called vacuum permeability, excuse me. Not vacuum permittivity, but vacuum permeability. Okay. All right. Good news is this won't take you long to collect the data once you set it up. Okay. So I'll kind of be walking around. I'll help you with this as needed. But read through the procedures there, and once you're ready to start collecting data, let me know, and I'll come and make sure you got everything set up right here. Otherwise, I think there's just stations around the edges here. So if you guys want to, stay with your tail partners, you guys can just go find one of those stations to work at when you're ready, and I'll let you guys get going. Okay. Are you all right finding the
Yeah.
work with? Okay. Yeah. It is. These are, this is like triple the normal slinky. Pretty straight, actually. Industrials.
It's so heavy.
Go down here.
That's not even like, yeah. No. No jumping rope though.
Well, all of it. You can make an accordion.
No, he was pretty chill.
And face purposes, yeah.
Yeah.
Stop it. Stop it.
Oh,
There we go. Thought he was gonna jump on. Oscar 9 was encouraging him.
I knew.
My body's.
My body's
Yes, no, I did show my.
Right, will be manually changed.
Yes.
All right, so what are we up to? We gotta count the coins.
You gotta count the quotas
We gotta
for a
count.
half piece.
Oh,
That's not how.
I know.
let me just grab a meter stick.
Yeah, that'd be good.
Are we gonna have to?